Okay, well, I'm going to try this video again. I just spent 15 minutes recording it with the microphone off, so I will do this again. Okay, so here I'm going to do the symmetric bending problem with the I-beam that we did in class, and we also did it with a single C-bar element, but I'm going to make a shell element mesh of the same problem just to show you how to do it, and then we will solve it and look at the results in HyperView, okay? So what we're going to do is we're going to create a shell element mesh and then apply SPC boundary conditions. But we will also create a RBE3 element, which is like a rigid element that's going to allow me to correctly transmit the point bending moments that we're using onto the whole face of the I-beam. It'll make more sense when I start to do it, okay? So I've already started with a couple things here. I've defined a aluminum material. Let's just go back here so you can see the properties. There's an aluminum material. I also have a component called I-beam. I created a load step, which is not much going on here, and a load collector called the bending load collector. We'll put everything into there, okay? So the first thing we're going to do is we're going to create the shell element mesh. Before I do that, we need to create a property card for the shell element. So just like the P-bar, P-bar-L, P-rod, we have to do a P-shell card. And that one's pretty easy. There's not much to it except defining the material and the thickness of the shell. So I'm going to go in here and right-click in the model window and do create a property. And I'm going to call it, it's 60 thou. It's 60 thou thick aluminum shell. So we'll give it a name. We'll pick the aluminum material. And the only thing we really have to type in is the thickness. And in this case, we know it's 0.06 inches. Okay? So that's it. There's other options here. We'll talk more about those later on. But for now, that's fine. Okay. So there we go. Now, if we click on the I-beam component, there's several ways of assigning the property onto the elements themselves. For shell elements, it's pretty easy to put them on a component. And if you see, if I click I-beam, you can see there's an option down here for property, and it's unspecified. So what we're going to do is we're going to specify it to equal that shell property, and that means that every element that's in this I-beam component will use that P shell card. Okay, so I think we're ready to go here. We're going to start making the mesh itself. Now what we're going to do is we're going to create lines on the I-beam cross section and then extrude those or drag them, which is what Hypermesh calls it, okay? So first we got to create the line. So I'm going to go under geometry. Now I created these nodes as we've done in the past just by typing the coordinates, right? So this is a 12-inch high by 10-inch wide I-beam. So we're going to go in and click on geometry and then lines, and then make sure you're set here to the linear nodes, and we're just going to pick, one at a time, right? And we're going to go this one to this one, hit enter, creates a line, this node to this node, create a line. Make them separate because we'll need to do that when we get the meshes so that they line up there on those edges. And there we go. Now we got the lines that define the cross section of the I-beam. I don't really need these temporary nodes anymore, so I'm going to go and delete them. Go under geometry, temp node, and then clear all. And then we're going to hit return. Okay, and now we're going to go drag these and make new elements. Okay. Actually, before they do that, well, that's fine. Let's just do it. So these are going to be not 1D elements, but 2-dimensional elements. So I'm going to click on 2D, and we're going to do line drag. So line drag, you can either drag existing elements, like 1-dimensional elements, and drag them into 2-dimensional elements. Or in our case, we're going to take lines and drag them into 2-dimensional elements. So I'm going to pick a line. Let's pick this lower flange here. And, oh, I I did line drag. I don't want line drag. I'm sorry, there's line drag, and we want just regular drag. So same concept, but this will allow me to drag it along the z-axis, right? And we're going to make it 48 inches long, and when we drag plus, there you go. There is a set of elements. Now you might not have 5 on this side, 48 on this side, and it might not look like this. You might have far fewer. One way you can change that, you can right click on these and change the number of nodes. Like for example, if I change this down to like 32, I'll get 32 nodes on this side. It's gonna make kind of not a great looking mesh, but there it is, okay? Or we could go back and change this to be something else, right? Mesh, there it is. Or the easiest thing we can do is you can go right here under element size and set the default element size to 1 and then just hit recalculate all. And I think you'll get the mesh that I got. There's lots of options you can do here. You can pick the types of elements. You can bias them so we put more elements onto one edge than another. So for example, I can change this bias to something like this. Well, I should do it this way, right? You can see it's pushing more elements to this edge than this edge. So there's lots of ways to do this. I don't like that. I'm just going to reject that. Oh, revert. Well, okay, let's just change this to 1. Recalculate all. So now I'm back to the unbiased. And we're going to mesh. Oh, wait, what happened? Let's go to density. What happened to density? 48, 48, 5, 5. Yeah, why did it do that? Oh, that's so weird. All the quads. We're going to make all quads. Don't worry about this. I'm just going to get it back. Why is it doing that? Oh, let's try this again. Okay. Okay. You probably don't have to do this. Let's drag plus. There it is. Okay. So, fine. Yeah. You can mess around with those things on your own, but this is fine. So, there we go. Okay, we'll return. So, we've meshed that. Now you can see it's got the color of the component, right? And we'll do the same process for each of the other ones. Set it so the element size is 1. That's good. The other way you can set the element size globally is if you go under preferences, there is an option for meshing options. And if you click on that, this will allow you to set the default element size. So I have it set at 1. And if you want to not mess around with it, clicking all the little mesh densities like we did before, you can just set that to 1 here and it'll work. Okay, so now we're back. We're going to drag this one. That looks good. And then the other 2 lines as well. This one. Okay, and this one. All right, so that looks great. Looks like we got a mesh. They're all nice uniform size, no distortions. But there actually is one little problem. As it turns out, that since we extruded these as separate lines, they're actually not connected down these seams where the web meets the flanges, okay? And, there's pros and cons as to whether it should automatically do that or not, but it doesn't. So we have to actually explicitly do that. So let's show how to do that. This happens a lot when you're importing other people's geometries in as well. So you have to do this operation quite frequently. So it's not bad to see how this goes here. The way we're going to do that is we're going to equivalence nodes that are really close to each other. So we're going to go into Tools and then pick on Edges. And what this is going to allow us to do is find nodes that are within 10,000ths of an inch of each other and equivalence those. Sometimes you need to make that number bigger or smaller. If you make it too big, it'll collapse small elements together into one node, and that's problematic. If it's too small, it might not find all the nodes that you want to equivalence. So you have to fool around with that a little bit. First, we're going to pick the component we want to equivalence, so it's the I-beam one. We only have 1. There it is. And to see if this tolerance is good enough, we're just going to do preview equivalence right here. And that'll show the nodes that it wants to equivalence. Well, that looks pretty good to me. So let's do it. So I'm going to just equivalence right here. And now they are equivalenced. And if you don't believe it, you can do preview equivalence again, and you'll see it doesn't show anything because they're all equivalenced, okay? I think if I make this really big, like 2 inches, and I do preview equivalence, you'll see the issue. You see it's grabbing all these elements, and you don't want that, okay? So we are not going to do that. I'm not going to do that. Let's reject that, okay? And go back. Okay, so I think that, let's just double check and show that the equivalence is there. So we go to Edges, Components, I-beam, Select, Preview Equivalence. Oh, because it's set to 2, that's way too much. 0.010. Preview Equivalence. So it didn't do it because I rejected. So equivalence, and then we return. There it is, and that's good. So now they're equivalenced. Where do we go? Let's just double check again. Edges, Components, I-beam, Select, Preview Equivalence. And now you can see nothing is there. So they're equivalents now. All right, so let's go and put first the fixed boundary condition. So we're going to put the SPCs on. So we go under Analysis, Constraints, and we're going to fix the nodes. So I'm going to fix the nodes on the left-hand side. You can pick them one at a time, like this. That's fine. But sometimes there are faster ways of doing this. So if you click under this big node button here, there's lots of options for picking entities, in this case nodes, by face, by group, by ID. I'm going to pick on plane. So I'm going to pick on plane, and then it gives you this 3-button option. So we're just going to pick 3 non-collinear nodes and select, and you see it picks all the nodes on those planes. So we're going to take those and fully fix all 6 degrees of freedom, and there you go. So that one's fixed. All right. Let's save this really quick. Now we have to apply the 2 bending moments onto this face here. So we have a little bit of an issue here, right? The bending moments are, those are point bending moments. So when we had the C bar element, this was easy, right? You just applied it onto the one node. But here we have a whole bunch of nodes that define that surface. So, if you just apply it to the middle node, it's going to just tweak the heck out of this one middle node. It's going to give you really high stresses there. That's not really what you want to do. In a sense, we want to distribute that bending moment, or whatever forces is, over this I-beam face or edge, if you will. So the most convenient way to do that is to use a specific type of element called an RBE3 element. It's a class of elements called a multiple point constraint as opposed to a single point constraint element. What they tend to do, and there's a couple of variants of those, and we'll talk more about those in another class, they allow you to distribute moments and forces and displacements over faces like we're trying to do here. So before we do that, what I'm going to do is create a little node out here and then create an RBE3 element from that node to all the nodes on this edge, and then use that node to apply the 2 moments, the moment around the X and the Y axis, okay? So first, let me create this node, okay? So I'm going to go to Geometry, create a node. We're going to type in the coordinates. So it's at X equal to 0, Y equal to 6, and then I'm going to use Z equals to 49. So 48 is this edge, and so 49 is just a little bit out of here. So change this to 0, 6, and 49, and then hit create. And you see we got a little node that's sitting out here. That's perfect. That's what we want. If the node goes right on here, sometimes it's tough to pick the correct node. You might accidentally pick the node on the I-beam itself, and then it'll be a little confused. But this is fine. It doesn't have to be right there. Out here is fine. Okay, so now I've got that node. Now we can create the RBE3 element. So these MPC elements, RBE3s, RBE2s, rigids, are all considered 1D elements. And so you click on the 1D box. And here you can see you got a button right here for RBE3. And so we're going to pick that. Now, you get an option here. We're going to make sure it's create. You have dependent node, and then it spans to a set of independent nodes. So in this case, the dependent node is the one we just created. So I'm going to select that. Now the independent node is going to be all the nodes on this I-beam face. So I'm going to use that, and I'm going to do the plane one again. So we're going to pick all the nodes on a plane. So this point, and this point. Select entities, and there they are. Create, and now you can see this. You've got this sort of spider webby looking thing that connects the node we created to all the nodes on that edge of the I-beam. So now what I'm going to do is I'm going to put the forces, or in our case the moments, on this node, and it's going to transmit those in a way that tries to keep it as a weighted rigid body through to that edge, okay? And it'll give us good results. All right, so before they do that, I'm going to just delete this temp node because I always don't like having those things hanging around. And so there we go. So now we're good. Now we got to just put the point moments on this node. So let's go under analysis, and then we're going to click moment, and we're going to click this node here. Now first we're going to put the 1,000 pound inch moment around the x-axis. So we're going to create that. So there it is. That's the right direction. Now we're going to do the y-axis moment. So the y-axis moment was negative 650, but you have to remember that was in that weird sign convention that the textbook uses. So it's actually, that's actually negative 650 is actually a positive 650 moment around the y-axis. So we're going to do that. Change this to 650. Pick the node and then create. Wait, what happened? Did it do it? Where is it? Looks like it didn't do it. Let's try that again. Create the node. Create. There it is. Okay, I don't know what happened. Maybe I missed the button. But you can see here, it has the two moments in the correct direction as we want. Okay, just don't be freaked out by that. I didn't put a negative 650 here because that's the sign convention. All right. So we're good to go here. We've got the boundary conditions. We've got the elements. The elements have their properties, the materials defined. So we should be good to go. Like I said, I already created a load step, and I set it to be a linear static, and I assigned the SPC and the loads to be the bending load collector. So you create those as we've done before and assign those, and we should be ready to go. So now I'm going to go into analysis and OptiStruct and run that. And let's see what happens. It should work. All right, it's solved. I don't think you can see that window, but it says it's solved. I didn't get any errors. If you get an error, you know, it could be a lot of things. Often it's you didn't assign the shell property to the elements or things like that, okay? But mine worked. So I'm going to hit results on the little output solver view, and that's going to start to load the model in Hyperview. I should just show that, right? So, yeah, whatever. Ignore me. I'm doing the. I'm getting the right window displayed in the capture program. Okay, so here we go. So this is our solved model in Hyperview. So it looks familiar. And Hyperview is a graphical way of seeing the results. Okay. Oh, I should probably do this so now you can see it. Okay. All right, it does a lot of things. The tool we're going to use here is to deform it and then also to shade it, right? So if you click this little icon here, with looks like a little colored flag, that displays what fields are being shown as colors on the elements. So it kicks down a bunch of stuff here. So we're going to look at the von Mises stress, right? So I'm going to pick, instead of displacement, we're going to pick element stresses. And we'll look at von Mises here. You can see there are lots of different ones we can do. We can do the triaxiality, the load parameter. We can do the stress components explicitly, the principal stresses, the Tresca stress, signed von Mises, whatever. So let's do von Mises, and then you hit apply, and here you can see it's showing the von Mises stress, okay? We also might like to see it deformed. Now the way to do that is go under deformed, that's this little icon here, and it allows us to see the deformation. Now here, the deformation scale to 1, so if I move the slider, it's barely moving, so you don't see it anymore. But if I change the scale value here from 1 to like 500, I think you'll see something. Maybe. Oh yeah, there it goes. So it's moving, right? If I slide this slider, it moves, and you can hit the little video and it animates it. You can make it go in different ways, you know. That's it wagging back and forth, and you can see how it's deforming both planes as we expected it to, right? Okay. I'm going to talk a lot more about how you can look at different types of stresses and whatnot, and we have to talk a little more about what's going on with shell elements, but you should be able at least to get that going, okay? Like I said, if you want to look at the principal stresses, let's do max in plane P1. And there it is, those are the principal stresses. Pretty much the bending stresses. We can look at the normal stresses in the Z direction, the CZ normal stresses, and use the global system here and apply, and you'll see we get the actual normal stresses in the Z direction. These are the bending stresses, okay? All right, let's stop there. Stop this, and we'll stop recording. Okay, well, before I stop recording, so make sure you might have to pause it, create the model, get it to run, and then at least look at the results in HyperView. We'll talk more about how you actually interpret these results in a class, okay?